All right, folks, maybe we get started. It is an absolute thrill to have Savas visiting us. He's a great friend to very many of us here. Certainly to me specifically, one of my very favorite people in the world, period, not just in physics. And so we're absolutely delighted you're here. Really looking forward to a fascinating talk. Savas will be here all week. And we look forward to rollicking physics discussions with him the whole time he's here. And he'll be telling us something extremely interesting about the cosmic neutrino background. Take it away, Savas.
Thank you. Yeah, I'm extremely happy to be here. I have many of my good friends here, and I'm trying to remember what was the last time I gave a talk here, and I'm having difficulty. I know that Edward was here, and Lima and Juan were in high school. And Natty was an outstanding phenomenologist. So I'm happy to be back for another talk. Most of my work throughout the years is about beyond the standard model. And this is, in fact, the first time I work on neutrinos. In fact, I used to make a lot of fun about working on neutrinos. A sure sign that in the end I would work on it. And it's the second time I work on something that is known to exist. The first was gravitational wave, designing a gravitational wave detector using atom interferometry 15 years ago. And this is the second. And so I'll talk about the cosmic neutrino background and how you can manipulate it to perhaps enhance somewhat the signals that it can produce. So a brief review, what is this, the C-nu-B? We all know the story. Neutrinos at very high temperatures were in thermal equilibrium. They fall out of thermal equilibrium when the temperature of the universe is around 3 or 4 MeV. And since that time, they have completely decoupled. The only thing they do is they fall in the gravitational field of the universe. And in so doing, they stretch their wavelength. So that's all they are doing. The present energy is about 10 to the minus 4 electron volts. The number density per helicity is roughly 50, and their mass is 0.1 eV. Notice that they're very non-relativistic. Their mass is 1,000 times smaller than their momentum. Nevertheless, they obey massless Fermi-Dirac distribution because that they inherited from the time when they were in equilibrium. The expectation for their abundance for the neutrino-antineutrino asymmetry is that it should be comparable to the baryons. This is well motivated by theories. If you try to build theories where they are not the same, sphalerons come in and equilibrate them. So we'll be assuming the expected value for the asymmetry is about 10 to the minus, few times 10 to the minus 9. This will not enter. I want you to keep this number in mind because we'll play with this number, be able to locally change it.
The 0.1 eV is just assuming that what we know about neutrino masses is not just delta m squared, but the overall m we know.
That's right. That's right. And there is a lower limit to the heaviest mass, which is like 0.15, and the laboratory limit coming from Catherine is 0.8 eV.
Right.
But I think the cosmological arguments are very convincing, so I'll go with that. In fact, the signals get better as the neutrino mass increases. But anyway, we'll take 0.1 eV, which is at the low end. Why it's important? I think everybody here knows why it's important. It's analogy with the CMB. We learned a lot of things, a lot of physics from the CMB, and there is a hope that if we manage to see the cosmic neutrino background and study it, we will learn a lot about both particle physics and possibly about cosmology. And this is essentially this slide summarizes some of the virtues. It gives us a picture of what the universe was. It probes, as far as particle physics, a whole new sector of the standard model, which has at least 3 flavors, and it has at least 7 parameters. And interesting, the neutrinos are the most abundant standard model species in the universe, together with the photons. The numbers accidentally happen to be comparable. And the C-nu-B neutrinos are the only non-relativistic neutrinos. Typical nuclear reactions, etc., produce the neutrinos far in excess of energy, far in excess of their 0.1 eV mass. And non-relativistic neutrinos are very interesting. For example, it may make a significant difference whether you have Dirac or Majorana particles, and that. So this is one of those situations where you could tell the difference of Dirac versus Majorana. Also, that's all. I'll come back to this later. Now, why the cosmic neutrino background is hard to see? To start with, the cross sections are small. And in spite of that, there's the heroic proposal of Ptolemy that may one day work and allow us to see the cosmic neutrino background through this charge current interaction proposed by Weinberg. In the past, several groups tried to see if coherent scattering can lead to significant enhancements. There are some enhancements, but they are not enough, and the forces that come from coherent scattering are significant, far smaller than the forces that I'm going to be talking about today. Okay. There is also some other effects of C-nu-B. C-nu-B couples to the C-nu-B neutrinos have a current, and there is a coupling of the neutrino current to matter that causes spins to precess. So the neutrino current acts like an effective magnetic field around which spins precess. This causes an energy difference of 10⁻47 eV between the parallel and the antiparallel state of the spin. And this is an extremely small energy difference, far smaller than the smallest energy difference that we measured. And so there is this effect due to Stodolsky. Is far, again, it's extremely small, very and far smaller than the effects that I'm going to be discussing. Okay, so now what we will focus on is C-nu-B forces on unpolarized macroscopic matter. Okay, so this will be and here is the interaction energy per unit volume for the interaction of neutrinos with matter. This is the current interaction, just the 0 component interaction we will be using. This interaction density gives rise to 2 potentials. For a single neutrino moving in matter, a single neutrino moving in matter sees such a potential, which is proportional to G Fermi times the density of matter, times some numerical factors that depend on the atom in question. These numerical factors will be important. For example, if you do experiments with materials that have different ZNA, you can use these to start differentiating flavors and start mapping out the flavors that existed at the time of C-nu-B decoupling. Notice that a very interesting statement is that the neutrino, the electron neutrino, feels a repulsive force from matter. So an electron neutrino that approaches matter will be repelled by it. Of course, the electron antineutrino does the opposite. On the other hand, the muon and tau neutrinos get attracted, but the mu and tau antineutrinos get repulsed. Okay. The reason for the difference between electron neutrinos and mu and tau is because mu and tau couple only through neutral currents, whereas the electron, there is a charge current interaction that contributes. So just remember, for our purpose, I won't be making continuous reference to mu and tau neutrinos. I'll mostly focus on, in what I'll be talking, I'll talk mostly about the electron neutrinos and antineutrinos, just to keep the language simple. Whatever I'll say about nu-e will apply to nu bars, nu bar mu tau, and vice versa. Okay. Conversely, if you have an atom that is in a bath of neutrinos, then it will experience a potential which is again proportional to G Fermi times the current of neutrinos and times the weak charge of the atom. The weak charge of the atom will be given by one of these formula. The characteristic, so to give you an idea of magnitude, the characteristic interaction energy of neutrino with matter is 10 to minus 14 electron volts. Okay, so an electron neutrino that approaches matter will see a potential barrier, a repulsive barrier of this height. Of course, the electron neutrino has a mass of 10 minus 6 eV. That's the energy of C nu B neutrinos. So that looks like a very tiny effect, but it will turn out not to be, as we'll talk later.
So can you explain a little where the 3Z minus A comes from?
Yes, I can tell you. So first, there are two contributions to nu-e, the neutral current and the charge current. And that's it. If you force the charge current, you get a force. And that's it.
And this is scattering off the electrons.
Yes, exactly right. Yeah. And this scatter of both electrons and nuclei. Yeah. Okay. To be specific, we'll assume that the neutrinos are Dirac particles and they're simultaneous eigenstates of mass and weak interactions. This is really for simplicity. If I didn't assume that I would have to express all my results in terms of mixing angles, and so I'll assume, and it's easy to translate. If you have your favorite mixing angles, you can translate these results about forces, etc., that will derive to any situation.
One of the neutrinos could be massless.
Yeah, I don't think it's excluded. Yeah.
So it doesn't.
No, it wouldn't play a role here. It wouldn't play a role, and you'll a little while later you'll see an explanation. No, it wouldn't play a role. Now, and in 1982, there was a famous no-go theorem that claimed that there are no C nu B forces on matter by Langacker et al. And by Habibu, Mayani. And essentially, the argument was based on the previous slide. If the interaction energy of an atom with a neutrino fluid is given by this, is proportional to the neutrino current, and the neutrino current is constant, then the force on the atom is zero. It wouldn't know where to point. And that was the theorem that sort of put a big stop to the field of looking for neutrino forces on matter. So now I'll talk about how you may be able to evade this no-go theorem, which is the first paper we wrote with Asimina back in December. And the basis of this paper, the physics can be understood very simply if you just remember this formula for the interaction energy of neutrino with matter, and also the statement that the electron neutrinos get repelled And of course, the electron-antineutrinos get attracted. It's convenient to also to express the results in the language of optics. There is an index, the interaction of neutrinos with matter cause an index of refraction of neutrinos, which differs from what? By this quantity delta, which will be very important, which is proportional to the interaction potential energy and goes like the mass over p nu squared. Okay, so if you had massless, anyway, you would get u over p for the index of refraction, which would be much smaller. This is amplified by m over p. So this is convenience. You can discuss everything in terms of potential, but since you can get additional information, intuition about from optics by using this expression. Okay, so here is a very brief intuitive picture of what will happen. Consider nu is, okay? Consider nu is and nu bars. A nu bar so top is outside the Earth, the pink is inside the Earth. An electron-antineutrino that hits the surface of the Earth will be attracted, so it will bend, its trajectory will bend away from the surface of contact. Conversely, a nu e that couples to the Earth will be repelled, so its trajectory will be pushed up. And it's quite clear from this that if you consider electron neutrinos that hit the surface of the Earth at smaller and smaller angles, eventually you will reach a point where there will be total reflection of the neutrinos. This total reflection of neutrinos is essentially responsible for the effect that I'm going to be talking about, this repulsion of electron neutrinos from the surface of the Earth will create essentially a traffic jam of nu-is as opposed to nu-baris, which will create an excess of electron neutrinos near the Earth, in the surface of the Earth, that we will show you how to estimate. To understand, first of all, this effect, let's first talk a one-dimensional analog. Instead of three-dimensional, let's say we have one dimension. This is the neutrinos energy, typical energy. This is the potential outside the Earth, inside the Earth. So there is a positive potential that the neutrino sees. If a neutrino has typical energy, then it will go straight through, it will change its velocity very little, because the potential is a tiny perturbation to the typical neutrino energy. If, though, a tiny fraction of neutrinos, in this case, like the ratio of these two numbers, 10 to the minus 8 fraction of neutrinos, will have small enough energy to hit the wall with energy below threshold, below the potential energy, and that will be reflected. And in the process of reflection, there will be an evanescent wave, or the wave that has penetrated. It's not a wave, the energy that has penetrated the barrier, and so you'll have an incident will give rise to a reflected and an evanescent wave at the same time. Okay, this is what happens in 1D, and as I said, it's a tiny fraction of neutrinos that would experience this. In 3D, things become a bit better, and the reason is that in 3 dimensions, there is additional degree of freedom, namely the angle at which you hit the surface of the Earth. So if the angle at which you hit the surface of the Earth is small enough so that the momentum perpendicular to the surface of the Earth is small, then that neutrino will not penetrate the Earth. And the condition that the momentum perpendicular is small enough that it won't penetrate the Earth is simply that the kinetic energy perpendicular to the surface is less than the potential energy inside. So you find that there is a critical momentum, which is square root of 2mu. Notice that this is a quantity proportional to root G Fermi, and it is of the order of 1/3 meters. So what this tells us is, of all the neutrinos that hit the Earth hit the Earth, a small fraction, those that hit the Earth at small enough angle, given by the ratio of the critical perpendicular momentum divided by the momentum, then if the neutrinos hit at small enough angle, which is given by this quantity, 10⁻⁴, then this fraction of momentum, this fraction of particles will be totally reflected. The scale of variation of course, by the way, this problem, of course, it's a very simple quantum mechanics problem that you can solve, and you find that the scale of variation of the distribution of neutrinos, both inside and outside, is given by the same scale, which is 1/3 meters. So the picture that you get for the distribution of neutrinos near the surface of the Earth is that inside the Earth, on the right is inside the Earth, outside the Earth, you have, depending on the neutrino mass, here I have the numbers for 0.15 eV, you have an excess of neutrinos minus antineutrinos that is maximal near the surface, and then it drops off with a characteristic length scale of 3 meters or so. What is the excess? Well, the excess for this mass is of the order of few times 10⁻⁴, which is about 10⁴ times bigger than the expected lepton number excess that comes from primordial baryogenesis. If the neutrinos were heavier, 0.8 eV, the result would be even more pronounced, and it would be more pronounced because the mass, the heavier the neutrino mass, the bigger all of these results get. The index of refraction scales like the mass, and the corresponding results get bigger. So this is the picture. So around the Earth, we have around the surface of the Earth, we have an excess of neutrinos. That is 100,000 times bigger than expected, and this opens new possibility for cosmic neutrinos detection. Now you can immediately do an estimate based on and compute the force on a macroscopic object. Let's say you have a tungsten sphere, 10 centimeters. Then the induced force on the tungsten sphere from this gradient on the surface of the Earth will be of the order of 10⁻31 newtons, which is pretty small, and we would like to try to do better by manipulating the neutrinos. Similar enhancement happens to the Stodolsky effect, namely the precession of a spin around a neutrino current. But again, the answer that one gets, 10⁻, for the torque exerted is still very small, 10⁻36 Newton meters. it's 10 to the 5 times bigger than before, but it's still quite small. So now, motivated by what the Earth does with essentially zero effort, the question is, can we do better by being clever and creating some matter configuration that will enhance the neutrino excess even more? So again, together with Mina, a couple of months ago, we made the following proposal. I'll first show you the picture and then tell you a few of the math. So what we are going to propose is something that looks like a sea-urchin. This is the sort of 3D picture of the sea-urchin, and that is the two-dimensional slice across it. So the sea-urchin will have rods of width W and some length L, oriented on the surface, along the surface, perpendicular to the surface of the sphere. And that will act as a diffraction phase grating, what's called diffraction phase grating in optics for neutrinos. And it will take, of course, it will make use of the wave nature of neutrinos. Okay, first, before we work out the full sea-urchin, we'll factorize it, or we'll into its basic element and show you how this works by first considering what happens to a wave when it encounters a single neutrino, a single rod. Okay, so a wave comes from the left. Part of the wave goes through the rod, and most of the wave goes outside the rod. Now, the part that goes through the rod, if you trace now the wavefront here, the part that goes through the rod gets an additional phase shift, which is proportional to this quantity delta. Delta, remember, is the index of refraction of neutrinos -1. So there is an additional phase shift here, whereas the part that goes outside doesn't experience any change. Now, what we would like to do is to compute the value, the value of the field at some point D, which is roughly near the front part of the rod. So this is not necessarily aligned with the rod, it would be a little off. And we want to compute the wave, the value of the neutrino wave at the point D. We want, in fact, to compute the value of the neutrino wave and subtract the corresponding value of for the antineutrinos and find what excess we get there. Now, to do this, we'll use one of the most beautiful things in theoretical physics in optics called the Kirchhoff integral theorem that tells you how to compute at a certain point D the value of a field if you know its value at the surface and there is nothing inside, it's empty inside. And the answer to this question is related to the famous Huygens principle from the 17th century, which Huygens was a contemporary of Newton, and he was the one who said that the way a wave propagates is that each point on the wavefront emits a wavelet. The different wavelets interfere with each other and give rise to the next wavefront. And that's how things move. So the Kirchhoff formula is a precise mathematical statement. Huygens' original formulation was very intuitive, then Fresnel improved it, and finally Kirchhoff derived it from Maxwell's equations. and we'll use the same, the analog thing for neutrinos, and you find that the value of the neutrino field has two parts. First of all, it has the plane wave part, the value of the neutrino fields at this point P, and then it has an additional contribution, which looks like looks like a diffraction pattern that the magnitude of that is proportional to delta, to the deviation of the index of refraction from 1. And it's also given by this Fresnel. This is like a Fresnel transform of a square. Okay, because I assume that the ends are squares. So that is the amplitude of the emitted wave. And so it looks something like this, a typical diffraction pattern. And now you do this because delta has opposite signs for neutrinos versus antineutrinos. You get a difference in the antineutrino minus neutrino axis that is first surfaces at a critical distance, which is the width squared over the wavelength. That critical distance is, you can understand very simply as follows. If you're very close to the rod, then you get a lot of short wavelength junk. If you go far enough, then all the points on the surface of the rod coherently add up and create this pattern. Okay, so the optimal distance to observe this axis is of order W squared over lambda. If you go much further than W squared over lambda, like to infinity, then diffraction, the wave will diffract and the intensity will dilute itself. So it's not it's not going to help. Oh, here is a picture of the diffraction pattern. What I was just saying. So this is Z is the distance from the surface of the rod. X is the coordinate perpendicular, and you see what I was telling you, that you get a pattern, and the pattern gets light colors means big excess. Then as the colors get darker, it means small excess, and then the sign flips. This is the excess of antineutrino minus neutrino. What gets focused by this rod is antineutrino minus neutrinos, because the antineutrinos have bigger than 1 index of refraction, so they sort of are like light. When they go through the rod, they sort of bend inwards. The neutrinos are the opposite. They get repelled, so they sort of spread outwards. So you get an excess of antineutrinos minus neutrinos. And this is the same pattern, but in the perpendicular direction, perpendicular to the rod. X and Y are the perpendicular. And here there is no surprise. You get a typical diffraction pattern. It looks a little more square because you took a square ending. You could have taken a circular end, and it was more symmetric anyway. And this, I'll go very rapidly. This is just showing you what happens when you average over all neutrino momenta to make sure this effect doesn't go away. Indeed, it doesn't go away, but you get rid of this small, short distance, junk that you had, small distance fluctuations, and again you get exactly similar behavior to before. You get. I should have pointed out here that the size of the effect is K delta lambda, because K is the momentum of the neutrino, delta is n minus 1, the index of refraction, and L is the length. So this is the excess phase accumulated when you go through the rod. So the whole effect, the whole excess, is proportional to K delta L. Obviously, the bigger you make L, the bigger an effect you get. So, now, a compound the compound neutrino diffractor that we propose is motivated by the fact that the cosmic neutrino background is not beamed, doesn't come from the left, it comes from all directions. So the best way to account for all incoming neutrinos is incorporates such a design, this sea-urchin design. Again, to maximize the signature, we put the distance of the ends of the rods from the center where we'll put the detector to be W squared over lambda. And it will turn out that the length L of the rod should be comparable to R. And you can argue for that too. The computation is significantly more subtle. There is something. Okay. Because most of the time, neutrinos don't come straight. They come at an angle between rods. So when you integrate over 4 pi to find to compute the effect of all neutrinos, there is highly non-trivial paths, etc. that I will not. Oh, now it doesn't move. Okay. We have the technician here. No, it has frozen. Ah, okay, okay. So anyway, so I won't go into more detail. So for a neutrino instant between two rods, the pattern changes. And this is a summary of what I said, that the optimal distance R is this, and we'll choose L to be of order R, the length of the rods to be of order of the radius of the sphere.
Why is it so subtle? I mean, it seems like roughly half of them are going between, roughly half of them are passing through.
Yeah.
So you would think that it's not.
It's
not
not very different. It's not very different, but you just have to do it right. You're right. And in fact, originally when we got excited, we estimated, just assume that they all go through rods paraxially, you know, and then you add up the effect of all the rods, and it was the same answer. But you know, we have to. The subtlety is that there can be cancellations, because in one case you get nu excess, in the other you nu bar excess, and anyway, it's easy enough to do correctly. So these are the index of refraction. Yes.
You also consider the effects of other rods on one. It's like the propagation. Let's say a neutrino could have passed through many rods before.
Oh yes, yes.
So it's not just
but
rising into a single rod.
No. And yeah, that's correct. So this is the numbers that we had to deal with for water. The index of refraction of neutrino is roughly 10⁻⁸. And then as you go to heavier elements, you get depleted uranium, which is of order of 3 times 10⁻⁷. But in between, you see iron is pretty good, but things like tungsten and depleted uranium, this is uranium-238, are good. So we have 3 proposals for this sea-urchin. We have a 2 meter, a 10 meter, and a 100 meter proposal. The 2 meter one, in fact, originally we had just a 10 meter proposal. And then we talked to Giorgio Grata, who is a great experimentalist in my department, who told us to use depleted uranium. And then I got, uranium, that's dangerous. I said, no, actually they use it for radiation safety. It's a very safe thing. Actually, they also use it in airplanes, very large wings. They put this for heavy mass to stabilize. Anyway, they use it for all kinds of things. So we added this. And then I gave such a talk at Stanford, and then Bob Laughlin said, "Oh, this is so big. You should go to 100 meters, propose a kilometer. And these things exist." And so we added 100. We didn't quite go to kilometers. It's easy to do the computation. But so we have 3 proposals. So roughly there is a 2 meter, a 10 meter, and 100 roughly meter with various widths and intergaps, etc.
How close is this picture to scale? Can you say what's the size of it?
Okay, so it's here.
Oh,
Let's say 2 meters the length, the width is 8 centimeters for this case.
so why is this a proposal? Why not just get a whole bunch of rods? Just do it like now, or.
Is there an experimentalist here? Is there an experimentalist
How long
here?
can it be? We have a lot of rods lying around.
In fact, this thing, 100 meters is, you can take steel from construction.
Yeah,
And 100 meters for construction, no problem.
I know many junkyards for which you
Yeah,
could easily.
and it
get,
doesn't
like,
have to be precise.
100. Yeah, right.
It's very funny because it doesn't have to be precise, whether it's square or circle or, we thought of, there's some very interesting things. We learned a lot about optics engineering and compound X-ray lenses. So we thought, what would happen if you put, spherical holes inside the rod? Okay, you would enhance it. In the end, we said, let's keep it simple. I'm sure people will be much smarter and find extra.
But did you tell us how much bigger over what you got from the Earth you got? Oh,
Yeah, it's 1,000 times bigger. Doing very little, as you see. This is not. Yeah. Okay, so what used to be, you'll see it at the end. I don't want to. Okay, so we have 3 proposals. And the Nunu-Bar asymmetry, this is just a picture of how the Nunu-Bar asymmetry looks. Again, light color means large, blue color means smaller. So the asymmetry has this spherical symmetric shape. And here, I'm sorry, this is a very busy slide. Here is the 2 meter, 10 meter, 100 meter. The only point I want to make is that for the 100 meter, you get an excess of about 10 to the minus 2 here. And the yellow line is for muon and tau neutrinos. They double more strongly, so they and the 10 to minus 2 becomes 5 times 10 to minus 3 if you go to 10 meters, and about 10 to minus 3 if you go to 2 meters. So it gives you an idea. And yellow lines are the nu mu and nu tau axis, and blue is the nu bar E axis. So the summary is, and this is original, we were just going to focus on this, the 10 meter proposal. The size of the asymmetry is this, this is the figure of merit for diffraction for this proposal. The size of the gradient is simply the width of the rod. And the size of the structure is where essentially you start getting the Fresnel constructive interference.
A second, what XD was?
Yeah, XD, I'm sorry, it's the distance. The distance, here is the rod. XD is the distance perpendicular. Yeah, so XD is really RD.
Oh, it's the radius.
After you say it's the distance from the center.
So it's like you're just holding the pointer there. It's already giving you some excess. I don't know, about a meter from the pointer of about, maybe 100 times smaller, 1,000 times smaller than the excess you're talking about.
It may be. Well, if you put many others, yeah, this may. Less experimental is, remember once you and I wanted to do an experiment with geckos?
I remember. That's people, the story. I don't want to hear more about
So, yeah.
But actually, what about, okay, yeah.
Okay. Now, so far, what we've done, we have, because our final aim is to try to find a way to discover the cosmic neutrino background. We factorize the problem to two parts. The first is to compute what the signal is, like the force, for example, in this case. And of course, the very important second question that is for experimentalists is how can we detect the signal?
So now you're using this gradient idea.
The gradient,
yeah, you're using
yeah.
the
The
force
whole
from
thing,
grad-
everything is the gradient idea. The other was, introduction. So here it is. Yeah, so here is the setup. So this is indeed the gradient idea. You take a detector made, the detector will be small. You could use gold for this if you wanted, let's say 10 centimeter sphere. So this blue is a little sphere. So you can put this sphere there. We put it on this white spot where the force is maximal, and you can try to compute the force. You can try to measure the force on it. So that's one proposal. So any idea about force measurements on objects of the order of a few centimeters could be applied to this. You could also convert this to a torsion balance. You can put two balls made out of different materials. One ball here and one ball there, say. And if they're made out of different materials, they experience different forces. So there will be a torque in the system of these two balls that you could measure. So those are two possibilities. The force, now we computed the force on 10 centimeter cube tungsten mass for just from neon neutrinos. If tau neutrinos have similar masses, then they'll double the force that I'm talking about. And this is for 100-meter iron structure.
What are the units there, Savas? In newtons? 10 to the minus what?
10 to the minus 28 is the, so this peak here is like 2 times 10 to the minus 28. So the force is, first of all, I didn't show this, that 5 orders of magnitude bigger than that compared from coherent scattering. Coherent scattering is just directly looking for the cross-section for, G Fermi square effects, take into account coherent scattering. And it's also 3 orders of magnitude bigger than what we get from the Earth. Okay, and this, this is simply the profile of the force acts. Okay. Here is the plot of the force. Again, the relevant units is now 10 to the minus 25 newtons, which is 1,000 times 10 to the minus 25 newtons. This simply shows that two things. First of all, if the neutrino mass was heavier, these effects would increase. So if for some reason you have doubts about the astrophysical neutrino mass of 0.1 and you're willing to go to 0.8, which is the laboratory limit, you would gain significantly in the force. But as I said, I believe this is the 0.1 is the right range. And again, yellow is from muon and blue is from electron and neutrinos. This dotted line is the standard quantum limit on, again, a tungsten mass. The standard quantum limit would be here, about 10 to the minus 28-ish. That's the standard quantum limit. So current experiments now that have been done are 8 orders of magnitude away from this.
Would you say where this standard quantum limit comes from?
Yeah, could I do it afterwards?
Sure, yeah. No problem.
Because let me do it. Okay. Now, the same idea can be applied to dark matter, in particular to the QCD axion. I don't want to spend too much time on this. You get the same setup with slightly different parameters. I'll skip this. The QCD axion couples to matter. It has couplings that are non-derivative that come about because it breaks shift invariance. QCD breaks shift invariance. So there are non-derivative couplings that give rise to an index of refraction. And that index of refraction essentially gives you, gives you such a coupling. That effectively this is an interaction for atoms times axion squared, you can think of it. So the potential energy of axions that we say dark matter axions around atoms behaves like this. It's proportional to the density of atoms, very similar to neutrinos. And this gives rise to the axion-induced force, which is now 10 to minus 25 Newton of that order of magnitude. For a similar, now the setup here is uranium. This is uranium with 10 meters size rods, 6 meter the central radius, 1 meter width, etc. So this is again a 10-meter structure with this slightly different than the one proposed for neutrinos, but it needn't be. This structure will also do a good job on neutrinos. And the reach of this proposal is shown here. If this red line, the present limits, there is no good laboratory limits here. This is the very famous terahertz regime, for which it's very hard to have detectors. So you can do good experiments, let's say ADMX. If you have macroscopic cavities, you can do, optics. I mean, in the EV range, but in the sub-EV range, in particular, the range of rotational molecular excitations, 10 to minus 3 electron volts, etc. There is no good, there is a lot of background just from things around us, so there's no good detectors there. So that's why there are no good limits, laboratory limits in this range. So this corresponds to an axion mass of 10 to minus 3 or so EV. It cuts off, you cannot go to arbitrary low axions because our computation are, the wavelength has to be shorter than the width of the rod. If you had bigger wavelength, actually you would need bigger rods and, I mean, you could still do it, but we just worked out the case for this. So in this case, instead of 10 minus 28, we get n minus 25 force. Again, by the standards, this may not be a very difficult experiment. Of course, there is a huge difference between telling experimentalists to look for something that is known to exist and telling them to look for the QCD axion at narrow parameter space. But since it's such a well-motivated dark matter theory, looking for the QCD axion would be the next best thing. So the conclusion is that the presence of the Earth can change the C/B distributions. We can change the C/B distribution and even the axion dark matter distribution. This, of course, sets a challenging target for new experiments The challenge is, okay, we have 8 orders of magnitude to go. But we have been there before several times. So I was looking to give you an example. I would love to have a plot which shows the search for gravitational waves over the last century. And I haven't found, I don't think so, no, I haven't found such a plot in 15 minutes of searching. So there may be one. That would have been an awesome parallel because gravitational waves were also known to exist. That's why so much effort went into them. But so I'll do the next best thing, which is tell you about things that we know, atomic clock accuracy. We went from the quartz clocks a long time ago where, you would lose a second every century. Now we would lose a second over the lifetime of the universe. That's how much progress there has been in atomic clocks. Of course, it was a lot of years. We're talking about 60-year time frame. And in fact, anyway, much of the progress, a lot of progress, like 6-7 orders of magnitude, happened much more recently, since 2000 or so. There has been tremendous progress with several technologies. As here you see the various technologies. And here is the evolution of electric dipole moment measurements. That's another great one that went from 10 to minus 19 to 10 to minus 30, approaching 10 to minus 10 minus 29 now. Of course, the wind detection, which I experienced myself in the early 80s, the limits were, they are not even shown here. They were not particularly impressive. Now we've pushed the frontier many orders of magnitude. So if there is a reasonable motivation, I think 8 orders of magnitude may be something experimentals will want to pursue. I realize that I'm planting seeds whose shade I will not see. But that's okay. I think it will be very cool when we see the universe when it was a second old. Thank you.
Any questions for Savas? Angela?
Yeah, I was wondering if you could talk a little bit more about how you're setting that inter-rod width. Is it sort of a naive thing where you want to pack in the rods as best as possible to maximize the density, or is it more subtle than that because the interference?
No, you can have you don't have to pack them very closely. You can leave a distance. I'll tell you what this design, as you know, experimentalists need AC signals. The signal I said now is DC, and that's very hard to detect if there is a signal. So there are ideas on, let me close this.
Actually, why don't you just spin it?
Okay, no. You mean the whole thing?
Well, or make it more
talking-
dilute. I mean, you don't have to make it as,
Yeah.
but again, you have an idea of what you're looking for. You have an idea for the length scale that you're looking for, so.
Yeah. I'll tell you an idea. I don't think, okay, here is an idea. One possibility, maybe, how can I do it?
Let me do it.
What? Oh, and, okay, whatever. So, several possibilities. First of all, spinning it would be very challenging, but the things that would be less challenging would be to so here is a configuration, etc. To move 2 of these rods, each adjacent pairs of rods together so as to change the distribution. So that could be done. Another idea that Giorgio Gratta suggested is the following. Instead of having the endpoints being squares, okay, make them circular and make them actually semicircular. So let's say you make it semicircular. Okay, so so it looks like this. Then he was suggesting you can put a rod. You can now spin each thing, each rod around such an axis, so as it changes as it goes around, it changes the pattern. So that's another idea. We were thinking of other ideas. I don't know how good they are to have them in sections. And then move them. So we didn't end up with anything. I think if an experiment is going to be proposed, they'll have to think about it even before they start, about how they are going to create to vary the signal. What's the most convenient? I like Giorgio's idea. In fact, that's good because he's interested in potentially pursuing this. So we'll see what he does. He doesn't think, by the way, the 10 meter is a big deal. He also says that if you want to get depleted uranium, you don't have to pay anything for it. Many reactors will transport it to you and give it because it has a bad name. Even though it's ultra safe, it has a bad name.
It's not like Giorgio's trying to convince you too much.
No, George actually used this for some of his experiments.
Our Hadron Collider at LEP was uranium absorber, also with Tevatron, one of them.
Oh, okay. See, I'm learning. The first time I read uranium, I thought you.
Tons.
I say 100 tons. Great.
1,400 tons. Yeah.
Okay.
Yeah. It was considered the gold standard for what we called compensating hadron calorimeters. So we used.
Yeah.
Instead of rods, could you have like holes in the eyes or?
Holes, yes, you can. I think it would be equivalent, even on the ground. We thought about it. The computations would be very similar. You can just dig in the ground holes and create a structure. The 10 meter would be straightforward. You can do that. Now you would, the index of refraction, if you just do it, wouldn't be as large.
Because silicon isn't as big as what you had.
That's right. And silicon is not as big, but so it's more like, it's approaching, we can go back to see what it was, but it's not as good. It's approaching, it's a few times 10 to minus 8, if I remember. Yeah, 2.5 times 10 to minus 8. So that's what it is. And water is less so, but this can definitely be done. And because ground, if it is easier, you can go 100 meters more easily in the ground.
The thing that the force is acting on is a little offset from the center, right? You're looking
Yes,
for.
yes. Mm-hmm.
So how does the 10 to the minus 25 newtons compare to van der Waals, all the usual stuff you would worry about?
This is
Far, really?
This is far. No, yeah. I mean, this is far from other objects.
No, it's far, but I'm talking about I'm just talking about it's far from other objects, but it's not far from. What's the distance to the? I mean, I thought it was meter scale distance from.
Yeah. That's what I meant. Far. I mean, van der Waals usually we talk it's. We talk about
at least Casimir would be one of the art of the fourth. I'm not sure it's is it that much. Minus 25 is really small.
I think it's very far. We can. And by the way, that's a problem. We know how to screen, but I don't think it is. But could be wrong. Yeah.
So we treat the baseline as the usual that you get from baryogenesis, but what about astrophysics? Like if you have these things passing through the disk, for example, they're going to encounter, you have a much lower density, but much larger propagation distances to accumulate some sort of asymmetry just by passing through interstellar medium, maybe occasionally stars, and things like that.
My hunch is that it will be very small effect because of the density, but by all means, I haven't estimated it. Too many fish we were frying. And I think it's and what would you do? Let's say there is some asymmetry. I'm sure there will be some effect. How you would measure it? What would it do?
Well, that's what I was asking, because I mean, it maybe, I don't know if this would be an additional enhancement. So is what you're showing is an enhancement that is, would this be on top of whatever the existing asymmetry is from right now? You're taking 10 to the -9 or so.
Yes.
If that were, say, from astrophysics 10 to the -8 or 7, this isn't an additional enhancement on top of that. This is a completely separate thing, if I understand correctly. So as long as that doesn't beat this, then it's irrelevant, I would say. As long as you don't get a higher enhancement than you would get from this sea-urchin.
I think it's very nice to put pencil on paper. We can discuss it afterwards and see. Yeah, because time is on the universe's side. So maybe.
From the neutrinos coming from the sun.
They're relativistic. So the index of refraction is small. Yeah. It's interesting because we thought, I mean, we had some other related ideas. The dream is, maybe we can detect reactor neutrinos. Maybe we can detect secret bomb neutrinos. Yeah, they are relativistic. Yeah.
Be very secret bombs.
Well,
Any other questions for Savas? One thing I forgot to say, we will be taking Savas to dinner tonight. Anyone interested in coming, please send me email. And we'll be gathering at around 6:30 in the lobby. If there are no other questions, let's thank Savas again for a fantastic talk.